有故事吗？哦，耶，还有故事诶，神奇。最喜欢听人家故事。我们这个想你有没有吃？你要吃吗？有 offer 吗？不懂，你去看以前我的钱。不要去那边等，那边很多人，夸张。如果他 offer 还可以等。我难得耶！啊？我可以不用。我以前会。
是一定要一个人一个 algorithm。可是我不知道讲它算不算复杂，他两个跟我都不知道复不复杂。
我就是不懂，我才拿一人一个。
因为我找到一个。
等下你也是问这个。
我找到一个 AES， 还有3个 GPU 3个 CPU。
跟我们走啊。
然后我就 text 他们有 reply 我，他听我。
整个人听不回应。你是要问他出我？收到了。
就问那个题目。
哦，听不可不可以？耶。我想去做节奏，可是我穿拖鞋。很晕啊？做了吗？今天很多，所以什么的做别的，做出来，做可以搞成这个 SP， 3个，很接近，厉害上下，他们问什么问题？我们是来表演，要不要请啊？那老师没有来。今天没有去啊？睡着了，今天真累。就是花钱的，这个的话，老师给他们看的，应该是怕是，或者是这个方面，如果是听静伟讲的话，1年是出2题算术，1题theory，然后theory会有什么空缺什么，就很容易啊。如果是老师换的话，就用来讲，1年来他老师讲的。第一课的 SPV， 第二课的那个 我们是 HP，算那个 SP 的，我们不做这个。哦，这个卫星没有看。我想做 FPS。Net profit value, net present value. 法律原来是一个，还有这个。 就加一块牛肉。今晚做多少？走啊，一起。是啊。这些如果不是，进出气。这个很卷。先做，比较快。
suggest using different algorithms. I know one is going to affect use maybe CNC. No, Huffman coding. Sorry, not Huffman. It's a wavelet. This wavelet.
其实如果你够苦的话是可以，像我要抓几个嘛，
找时间对
只是如果你到时候做不出个别杂就是找不到说出来说做简单的上课。
The school is everywhere. Very easily find. Okay, we'll discuss it later because right now it's lecture. We'll discuss it. Okay, I don't have a mic, I don't have a loud voice, so you sit in front there because otherwise you will not be able to hear what I say.
老师给没有一个吧
I mean, sit closer. I don't have a loud voice. And there's no speaker here. Sorry, there's no microphone. I mean, you sit nearer so that you can hear what I say. Okay, this part is quite important because I know that it's going to come out in the exam. Final exam as well as tests. Yeah. This part, I know it will come out of the exam. Microgravity. Okay, deadlock. Okay, this part here. Okay, so what is deadlock? Deadlock is two or more processes that they are waiting indefinitely for one another. Okay? And because they cannot attain the request, that's why they get into blocking state. Okay, it means a simple example. Let's say this is track number 0. Okay? It has a let's say for example this is the request. Let's say for example this is the resource 0. This is the resource 1. Let's put resource as a box. A, B, and this is the the process or the track, let's call it process 0, and here is process 1. Okay? Now, let's use some notation. This notation you see in the next slide, but I'll show you now. So if let's say P1 own this RA, so we draw an arrow like this. Okay? So P1 means process 1. This is the resource. Okay? We acquire this resource, therefore P1 hold this R1. Okay? So means hold. Okay? P1 hold this RA. I should say helped by, because the arrow shows that you are helped by. The resource RA is helped by P1. Now suppose this also is helped by P0. Help, that means you manage to attain it. You acquire the resource, and of course you use mutex. You use the mutex and you acquire successfully. So this one is protected by, let's say, mutex. This is protected by mutex A, so you acquire the mutex. Okay, this you also acquire the mutex and it's successful. That means this resource is helped by P0. This one helped by P1 using this mutex. So there are two mutexes here. And then after that, while it is holding this, it's also requesting. So here I draw another arrow. If the arrow coming from process to the resource, that means it's request. Okay? Request, that means it try to acquire this mutex B. Okay? If we manage to acquire mutex B, that means it owns this. But this is already owned by P1. That means P0. So P0 managed to acquire mutex B, therefore it holds this B1. Okay? And this is also trying to request to attain this resource. So you can see that now they are in deadlock. Okay? Why? So RA is a resource held by P1. So mutex is acquired already by P1. Okay? Now P0 also managed to acquire RB. They help this, that means it acquired, successfully acquired. So this one acquired. Okay? And then P1 tried to request, but it tried to request the resource that is held by P0. The same thing, this guy also tried to request a resource held by P1. Now, this will be blocked, this will be blocked. Right now, both of them cannot progress. Okay? So you can see both of them cannot progress. Okay? P1 help or holds resource RA. So there's a 1. Number 2, P0 holds resource RB. Okay? And then P1 tries to acquire RB, but fail. Okay? Why it got blocked? Because it's already held by P0. RB is held by P0. Now P0, it tries to acquire RA. Okay, but not blocked as well. You can see that both of them get blocked. This one get blocked, this one get blocked. And in order to release this, okay, P0 and P1 needs to run, right? But both of them get blocked. So how are they going to release the resources? They cannot release the resources. Now you come into a deadlock. So this is deadlock. Deadlock means you cannot progress. And you're stuck there forever. And this is a very serious problem. Okay? You don't want to have this kind of problem. Okay? So how do you overcome this? If let's say, of course, you will get into this situation, right? You hold this, and then the other one requests, and you get the data. Of course, this one is only two. You have situation where you have more threads, more processors. So I draw, let's put R0, and then this one is P0, R1, P1, R2, P2, R3, P3. Okay. Let's see a larger number of processes or threads. Okay. So this one is helped by this. 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 Okay. Right? Now suppose this is requesting. No, this one owned by this one owned by this one is owned by this. Right? And of course they are protected by mutex. So mutex 0, mutex 1, mutex 2, mutex 3. Okay? Now you try to acquire this mutex and you'll get blocked because it's already owned. Right? This one also saying you try to request, but this one is already owned, so you get blocked as well. And this guy tried to acquire, but this is owned by P2, and therefore he also get blocked. It's also the same thing. So this also a blocked. But it involves more. It involves how many processes? P0, P1, P2, P3. Okay? So if anything that cause them to be in this kind of situation where they're waiting for one another's resources, this is called deadlock. And this one is serious because once you get into deadlock, you cannot recover. The only way to recover is to kill all the processes, that means terminate all the processes, or reboot your system.
Cannot just kill one process.
Yeah, you can kill one. Let's say you kill this guy, right? But then this process somehow might change the state of the R2, right? So this state is incomplete because let's say read, modify, write. You managed to read, modify, but haven't write.
So need to roll back.
You have to roll back. So that's why your database you have rollback. Okay, but in this system we don't have. This database is a way to actually, it has a very powerful mechanism. It can roll back and then it can restart. Whereas our program normally we don't have that kind of features. Okay? Because database is meant for this kind of situation. That's why they know it's going to happen. So they create the database with rollback feature inside it. Okay? And they can kill the process. And when they kill the process, they can recover without shutting down the system and restart the whole thing. Okay, so database actually is a very resilient system, and it's built to overcome this one problem. But our processes normally we don't have this. You write a program, do you have any code that can roll back? No, you don't have any code that able to roll back, right? So normally we don't have that in mind. That's why this deadlock is very serious problem. Okay, so this is involving only two processes or two threads. This one involving more threads or more processes. Okay, so there's deadlock. Now let's see how deadlock happens. Now, in order to protect these resources, we're going to use two different mutex or two binaries of code. So this mutex A is going to protect this. Mutex B is going to protect that, right? So if you write program this way, then you find out that they will get into deadlock. Okay? I think this one is not clear. Let me write it down. So I'm going to write the code for this. Okay? So P0, when it runs, Okay, I'm not going to write the C language code, I'm going to write just the serial code. Okay? So suppose it wait. Wait means doing a down. Wait for mutex A. Okay? That means, sorry, mutex B. Okay? Then after that, because nobody owns it, so it's successfully acquired. That means RB is owned by P0. Okay, so when I wait for mutex B, if I succeeded, I get past. That means I successfully acquire mutex B, meaning that right now I own resource B. Okay, then it will, once it is done that, then it requests. It make a request. So this one is successful, and it made a request. Get mutex A. Right? Now this one might fail. Okay? If it succeed, that means P1 has not acquired mutex A. Okay? So here I can process resource A and B, RA and RB. Okay? And then after that I release K signal. Actually, I shouldn't call it. Okay, I just call it signal. Actually, here it means release. Release mutex A, and then release mutex B. Okay. Now this one also the same thing. I wait for mutex A. Wait for mutex B. And then also I do some processing, but different process maybe. Okay, I process the resources, RA and RB, but in a different manner. Okay, say, and then I signal mutex B, and then signal mutex B. Okay, this one will cause race condition. Oh, sorry, deadlock, not race condition. Deadlock. Why? Possibly, not necessary, possibly. And how does it happen? P0 wait, and it succeeded. That means it acquired mutex B. Okay? Let's say, for example, right now P1 also execute, and it will wait for mutex A. And mutex A, nobody acquired, right? So it will succeed as well. So this guy succeed, this guy succeed. So by the time he reach here, he already owned resource B. This guy already owned resource A. Okay? Now once you execute this wait, now because this P1 already acquired mutex A, so here it get locked. Okay? The same thing, when you reach here, because P0 already executed, so you get blocked as well. So when you get blocked, this one is the race condition, deadlock. During this situation, here is deadlock. You see that? Now, of course, I say potentially, it means that it can happen like this. Now, if let's say P0 is passed, you execute this, before P1 execute this one. Now, succeed, this one it will succeed as well, so no problem. Okay, it means that only in certain situations deadlock can happen. For example, if this is fast, but then it is slow to get this, but this one is fast, and therefore it gets blocked. And because it got blocked, you already acquired this guy also will get blocked. Okay, so you get into deadlock situation. But if P0 is extremely fast, you acquire this, and then you acquire this before this guy acquired, then it's okay. Because acquire, it succeeded, so you enter into critical region. Whereas this guy, when he comes in, he tried to acquire this, but because he already acquired by P0, right? So he get blocked in. But this guy get past this stage, and therefore there's no deadlock. And you manage to process this, and then signal. Once you signal, you wake up, and then you signal again. Okay, you acquire, wait for it, but you succeeded, and then here also will succeed. Okay, because it's signal, right? So it succeed. And then you process A and B, and then you release G. So in that kind of situation, no deadlock. Okay? So deadlock only happens when that kind of situation, like what I mentioned, acquire this, and this guy also acquire. Then you get into deadlock. Okay? But because the possibility of it happening, this is not desirable because it can happen anytime. You cannot expect that this guy always fast or this guy is always fast, right? So how do we overcome this? Can we overcome this deadlock? That means whatever condition, whoever fast, it doesn't matter. But we don't want deadlock.
Set the timeout?
Yeah, you can set the timeout, but no, it doesn't work that way because new text don't have a timeout. Okay, there's a way to overcome it. I'll erase this. Okay, let's have a look how we overcome it. Actually, it's very simple. What you do is you just make sure that if you look carefully here, the way I acquire the resources is the reverse. You see, right? D and then A. And then this one is A and then P. Okay? What we need to do is we just acquire them in the same sequence. If you do that, then deadlock will never happen. Okay? So let's see. P0, P1. I just changed the order. I just changed the order. So right now, instead of wait mutex B, I wait mutex A here. Okay, and then wait mutex B. And then I process both RA and RB. And then I signal. Mutex A, signal mutex B. Okay, the same thing here. Here I wait, but I will wait for mutex A also in the same sequence. Okay, and this I process, but in a different way, maybe. Process RA and RB. Okay, and then signal. Okay, if we do this, then race condition will never happen. No matter who is slow, who is fast, it doesn't matter. Okay, let's say. If let's say P0 is fast, it will execute first, right? It will acquire mutex A. And then it tried to acquire mutex B, it will succeed because A and B, nobody has acquired yet, so it succeeded, no problem. And if let's say this guy is slow, when it comes in, you get blocked here. Okay, but this guy is not blocked. It proceeds and then it managed to signal, and therefore this guy can pass. Okay? Now let's say, for example, this guy is fast, this guy is equally fast as well. Okay? Comes in to wait, and then this guy comes, to wait, but he will succeed because nobody acquired mutex A, so he will move on. And before he acquired this guy comes in. When he acquired mutex A, he will get blocked because P0 succeeded in the acquisition. Sorry, can I call you back because I'm in the lecture now? Okay. Next. Okay.
做什么？这个会怎么会乱？因为你这边一样，然后这样是 A，然后这个一开始就是 A， 变这个拿着，然后这个就这样子。
Okay, so you can see no matter who is fast, okay, one of them will acquire the mutex A first, okay? And the other one, if it is slightly slower, then when you try to acquire it, you get blocked. If this guy is faster, you acquire first, and this guy will get blocked. And somehow, you will not manage to get to the second stage to block, to acquire the other resources, and therefore, you'll never get into a deadlock. You understand? Okay? So whenever you acquire the mutex, you have to acquire more than one mutex. In this case here, most of the time you acquire only one mutex, but here because you are using two resources, and each one of them is protected by different mutexes. Okay? So in order to use RA and RB together, you have to acquire both. Okay? So mutex A and then mutex B. If you happen to get into this kind of situation, make sure that you acquire in the same sequence. Here you acquire A and B. Here also you acquire A and B. Okay? Make sure that you acquire in the same sequence. All right. How do we ensure that we get into this kind of situation? Because sometimes you put A and B, or you give a name. Let's say, for example, this guy is printer. Let's say we don't use A and B, we use printer, mutex, and this one is, let's say, monitor or projector, mutex. Printer, mutex, projector, monitor, mutex. Okay? And we know that we have to share the resources among the process, right? We cannot two process actually print at the same time, otherwise they print garbage. The same thing for your monitor. Okay, if you are printing something onto the monitor, you need to acquire the monitor first, then only print. Otherwise you receive garbage, just like what we have seen in our practical, right? So if you, let's say you have this kind of situation, then you have to acquire in the same sequence. You cannot interchange them, otherwise you get into data, right? But the problem is this: if let's say you've got so many resources protected by different methods, how do you order them? How do you know that monitor first, printer next? Right? So normally what we do is we give a number. Okay, we give a number at the back there. No matter what is in front here, we always give a number. And this number is always unique. Okay? Let's say this one is 0, this one is 1. Same thing, this one is 0, this one is 1. Okay? So whenever you want to acquire the mutex, you look at the number. Okay? You always acquire in the ascending order or descending order. Okay? By giving a number like this, if let's say it's ascending order, you must make sure that 0 comes first, 1 later. Okay? If the descending order, you must make sure that it's 1 first, then only 0. You understand? Okay, let's say you got a resource A. Resource A is protected by mutex number 1, let's say. Resource B protected by mutex 2. Resource C mutex 3. And resource D mutex 4. Okay, let's say for example, this is another example, not the same as this. And let's see if I have all this, and I have processes that need to use some of the resources. And how do I make sure that there's no race condition? Okay. Let's say P0 needs to use B and D. Okay, B and D. And P1 needs to use, let's say, A and C. Okay? And P2, that means process 2, needs to use D and A. Okay? And then process 3 needs to use, let's say, A, B, and D. And let's say it's that. Alright? So how does all these resources should acquire the resources? Okay, let's say in ascending order, right? We choose ascending order. That is 1, 2, 3, 4. Okay, in that order. So we know that this one is B and D. We should acquire B first. Okay, because B is mutex 2, right? So acquire, that means you have to wait for RA, so RB, mutex 2. So 2, yeah, 2. Okay, and then only D. RD, mutex 4. Right? Yeah. Okay, you have to acquire it this way. That means in ascending order. So 2 first, then only 4. Okay, how about A and C? A and C, you wait for RA, you types 1, because 1 is smaller than 3, right? So it has to wait for RA first, then only RC. Mutex. It must be 1 and then 3. You cannot be 3 and 1. Okay? How about this one? The same thing. You must acquire A first. You cannot acquire D. If you acquire D, then potentially you can create deadlock here. Okay? This guy can cause the deadlock. So you have to acquire A first. Mutex 1, then only wait for RD, mutex 2. Okay, this guy has to acquire 3 of them, so it must be wait RA, and then wait RD, because D is the second one, and wait RD, because D is number 4. So this 4, this is 2, this 1. Okay? This is 4. Right? So you must acquire in ascending, let's say you choose ascending order, so it's 2, 4, 1, 3, 1, 4, this one 1, 2, 4. Okay? Then guarantee this one will not cause any deadlock. Okay? Even though you got all sort of combination, you don't have to worry because they are in order. Okay? It will never generate any deadlock. But if one of them, you interchange them, then potentially it can cause deadlock. Okay? Now, how about the releasing the resources, which I use signal here? Does it matter? So here we process the data, right? So we process here RB and RD. Now how do you release? Do you need to release in certain order? Do you need to release RD first, then RD, or RD first, then RD? Okay, releasing actually no problem. You can release any one of them. You can release RD first, or you can release RD first. It will not cause any deadlock. Okay? The deadlock happens only for the weight. It must be in certain order. So if you choose ascending order, make sure that it's all ascending order. Okay? If you choose descending order, that means 4 first, then only 2. Then here must be 3 first, then only 1. Then here must be 4, then 1. So here will be 4, 2, 1. Okay? You have to reverse the whole thing. But releasing, you don't have to worry because in any order, it will never cause any risk condition. Okay? So that is the deadlock. Now the starvation, I'll keep it to later part because starvation is some form of problem as well. It's not as bad as deadlock because in starvation it's just you're starved. I mean the thread or the process is starved, but it's not blocked forever. That means somehow it's able to execute, but it does not have the processing power to process. That means sometimes it gets, sometimes it doesn't get. That's why we call it starvation. That means the process is not given enough CPU to actually execute. Okay? Okay, deadlock is different. Deadlock is you block one another and therefore all cannot progress. Okay, starvation means some is starved, some allowed to be to progress, but the rest who does not have the privilege, they will not get the CPU attention. Okay, that will be discussed later. That is starvation. Okay, this cause deadlock. It doesn't cause starvation. Starvation is a different problem, and I'm not sure why they put starvation here because there's no starvation. I don't see any starvation in this kind of situation. Here is only deadlock. Okay, here actually explain what I explained to you just now. All right. So we see. Mutex, if you are not careful, you can create problems. Like for example, in this case, this one can cause deadlock. And last week I also mentioned to you, if you do it this way, then no problem. If you do it this way, you got problem because you signal first, then only wait. By right, you should wait first, then only signal, right? You cannot release, then only acquire. It's wrong sequence, right? So They can cause problem. What kind of problem? Because race condition. Why? Because the signal, nobody wait, and everybody signal, and everybody get into the critical region, and they can cause race condition. So all of them will get into critical region and therefore cause race condition. How about this one? Everybody is waiting first. Wait and then wait. Okay, this one, all of them will be blocked. That means all of them will get into deadlock. Right? Last week I showed you more examples. This one only 3. Last week I think I showed you 5 or 6. Okay? If you omit one of them, let's say you omit wait or you omit the signal, then you'll get into the same situation as the first one, where everybody managed to get into the critical section, and then they will cause race condition. Okay? So there are a lot of problems with this semaphore, and of course, if you're not careful, especially if you are beginners, you get into this kind of trouble, right? So how do we overcome this? Okay, this is the last slide. How do we overcome this? Okay, we go to practical 5. Lecture 5. We solve this using monitor. Okay. So monitor is something like counting semaphore, binary semaphore or mutex. The only difference is the way we construct the protection or the critical region, or we protect the critical region. We write it in a different way. Okay? Normally it is bind together with the language. That means the program language has its own construct, that means a way to write the program, so that you don't make this kind of mistake. For example, you wait, then only you release. Okay? That's the correct one. But you might make mistake. You signal first, then only wait. Okay? Or you wait and wait. Or you signal. Okay? Or you signal, you forget to you wait, forget to signal. Or you signal but you forget to wait. Okay? So how does programming language solve this problem? They introduce this monitor. In Java, we write it this way. So if this is the method, let's say I call it method, let's say void method. Inside the class, I don't write in full. So you have a class, and inside the class you got a method. Let's call it what method 1. Okay. And normally you put a bracket like this, and then you put your code inside there, right? So before you put this, you write synchronize here. Okay? If you put this keyword synchronize, that means this whole block here will be critical region or critical section. Okay? So if you make a call to get into here successfully, you will lock first before you execute. When you get out, you will unlock. So here you don't see wait and signal, and therefore you don't make any mistake. Right? Because when you enter, it will lock for you. When you get out from here, you will unlock. Okay? It also helps. Let's say, for example, you got exception, right? Exception. When the exception halfway, you will actually get interrupted. This method get interrupted, and you get out halfway when you execute it. And in that condition, also this synchronize will help you release it. So even though you did not manage to get to the end yet, let's say there's an exception happening in the middle, it will also get released for you. So that means synchronize using this monitor technique, this way we call monitor. Okay? It helps simplify and make your programming much easier. Okay? Now in C++ we have a way also, but it's not like this, not as good as Java. Java has a keyword where we introduce some monitor. In C++ we use no text as well, we use lock. I'll show to you someday. Maybe next week, because we're going to cover practical 5. In practical 5, I'll show to you how C++ write the monitor. Okay? I'll show to you also the binary semaphore mutex, and then how we implement monitor in C++. Okay? It's not as beautiful as Java, because Java we got this too. Okay? C++ we don't have that, so we have to implement it in another way. Okay? But the concept is the same, right? Once you enter into this body, it will lock it for you. Once you get out, you unlock it for you, so you will not make any mistake. Okay? So the question here is, do I use monitor or do I use this binary semaphore or mutex or counting semaphore? It depends. Monitor, if you use it for most of the problem, you can solve using monitor. But sometimes you need more control. Monitor cannot provide you that. Okay? So if you need some more details that you need to do, it cannot be done in monitor, then you have to use counting semaphore. Okay? So counting semaphore is actually the raw type of mutual exclusion. But then it is not easy to write correctly, so we use monitor. But in cases that monitor cannot help, then we go back to counting semaphore or binary semaphore. Okay? So most of the time, it's best to use monitor. Okay, I'll skip all this because this one basically explaining in detail how it is done. And here it talk about conditional variable. I'll show it to you in practical 6 easier, because if I explain here, I don't think you will understand what conditional variable means. In the exercise, we will see this conditional variable in C++. Okay, so I finished all that, which is mutual exclusion. And now we come to another mutual exclusion. Just now the mutual exclusion is on a single computer. Okay? What happens if, let's say, that means this is a single computer and the resources is inside the computer. For example, in this case here, you got print, maybe printer is connected to it, monitor, right? Okay? So your resources here is connected to this computer, and the monitor is also connected to this computer, right? So it's a single system. This is a single system. Now in a single system, then we use whatever that I've shown to you, binary semaphore, counting semaphore, mutex, to protect the resources. But what happens if, let's say, it is not a single system? You have distributed system. Okay, distributed system means you got computers all are separately quite far away, and they are connected through the internet, let's say, for example. So if you need mutual exclusion, that means you need to ensure that the resources is used only by a single entity at any time. Then you have to use a different kind of mutual exclusion. We use one of the solution is token passing. Okay, so token passing algorithm is one of the simplest way, and I'm going to show you two algorithms. The first one is called Suzuki Kasami by two Japanese computer scientists, and the other one is Raymond's algorithm. Okay, Raymond is another computer scientist. He is Australian, so he came up with that idea after Suzuki Kasami, because there's a problem there. So he introduced his own idea, and these two are the most common one that you hear if you go to the internet. Token passing algorithm, okay, for distributed system. So whatever we have learned is for single system, but for distributed system we have to use one of these algorithms. One of them is called token passing algorithm. Okay, so token passing algorithm is a set of algorithms. So Suzuki Kasami is one of the algorithms. Okay. Now I'm not going to use this slide here because it's quite confusing. You see some equation here and then a lot of writing, but I'm going to take notice of certain part. You see there's a request here and there's a last here, right? So these are two arrays which we're going to talk about. So there are three things that we need to talk about. First is the request array, which is this one. And the second one is the last array. Okay? And the third one is the queue. Okay? These are the three elements that we're going to talk about. Right? Now, before I go into the details, okay, I'll show to you a video first, a YouTube video, which I'm going to play later on. And I'm going to use that as a tool to explain to you. Okay? Okay, so the whole idea is this. We need to protect the resources. Let's say, for example, database. Okay? Database is used in a distributed manner. And in database, you must make sure that only one resources change the data inside the database, right? So you cannot have many entities that change the database. Because the database is used by multiple entities in the network, so somehow you need to synchronize all of these nodes. Make sure that only one entity accesses into the database. Okay? So let's call this a node. Let's say node A and node B. Let's see. And let's say now one. Right? So say this is the resource, is the database. Now whoever own this token, there's only one token, and they pass this token. That's why it's called token passing. Okay, the idea is whoever owns a token will be able to use this database. Only one person, and there's only one token. So you got one token only. Okay, the rules. There's only one token, and whoever owns the token has the right. That has the right to critical section. Yeah, put CS here, critical section. The critical section is basically a code needs to be run in mutual exclusion manner, especially when you access into the database, right? So a piece of code where you access into the database, and this is shared, and therefore you need to protect it. Okay? So we use token in order to protect this resource. And we pass this token around. Whoever needs to use it, we pass it. Let's say, for example, let's say A wants to use it. It needs to own this token first. You have to request it if it doesn't have. You have to request from, let's say, node B. Let's say node B is holding it. Node A needs to request from node B, and node B needs to pass it to node A first. Now, if node A receives it, that means node A has the right to use it. Nobody else can use it. Okay? The same thing, if let's say node D wants it, he has to ask from node A, and when node A will pass it to node D, and once node D has it, then it will own this database and can use the database. It can enter into the critical section and do the process. Okay? So that's why it's called token passing. Okay? This algorithm is very simple. And what we need is, we need request array, last array, and the last one is queue. Okay? Okay, let's look at this video. Okay, this video do not have sorry, I'll just skip it. Okay, it doesn't have any sound there. It's just wording on it. Okay, let's start with this. Let's say we got 5 nodes. 1, 2, 3, 4, 5. 5 cities. 5 sites, sorry. 5 sites. Okay, each one of them is called node. And what we need is each of them to have their own request array. Okay, this is the request array. We call it RM. And this array is the size is the size of the sites. If let's say the site is 5, then the array element, the array size needs to be 5 as well. Okay? That means each element inside here will correspond to the site. That means element 1 will be site number 1, element 2 will be belonging to site number 2, and so on and so forth. Okay? So this request is to keep track of who is requesting the token. Because at any time, let's say node C and node D request it, right? But how do we keep track? Who is requesting what? Right? Or who is requesting the token? So we keep this buffer or this array to find out or to realize who is the one that is asking for the token. Right? So that is the use of this array. Okay, let's move on. Okay, so each one of them will keep track. It will keep track of one another. Okay, so right now all of them will start with 0. So this 0 here is actually a sequence number. Okay, you can see that here it means request. Request means I ask. Okay, now you need to differentiate between the new request and the old request. That's why you give number. The larger the request number, the later it is. Okay, let's say the request number is 5, and you compare with another request. Let's say you receive another request. That request is 3. You know that request 5 is the latest one. Request 3 that comes is the old one. You have to discard it. Okay, so this request number is to find out who is requesting it and when that request is issued. Okay, the higher the number, the later it is. That means the latest it is. So all of them, we start with request number 0. Okay. Okay. Another array that it has to keep is this last array. It's called LN. This last array also of the size 5 as well. If let's say, for example, there are 5 sites, right? Here should be 5 as well. Initially it's empty, and the queue here is empty as well. Okay, the queue is storing who is actually requesting it. Okay, and we will serve according to the elements, the site name that appears in the queue. Okay, whoever comes first, we will be served first. Okay. Okay, let's look at the example. Before we go into example, one thing that we need to make sure is whatever we receive the request from any of this site here, we need to differentiate between new one and old one. Okay, so we use this number to identify it. If let's say the number appeared inside your array is higher than the one that you received, okay, this sequence number is the one that the node sent to you. Okay? Let's say you already have inside here. Okay, I'm not going to put ABC, I'm going to put 1, 2, 3 to correspond to that. Okay, let's say 4. So I got this 0, this 1, because I started 1, 2, 3, 4, that's it. Okay, so let's say node 4 send a request. Okay, it sent a request message, and it tell this node 2 its own ID 4, and then you put here, let's say number 1, and here of course it starts with 0, right? Okay, so when I see a 1, node 2 see a 1, it knows that this is the latest one because what it has inside the request array is 0. Okay, so if you see what you have is bigger than what you receive, that means that is old. Okay, but then if you see that it is less, that means you know that it's not old, it's not outdated. Okay, so you accept it. So you accept if let's say the number is bigger. So you can see here, this is 1, it's bigger than what you have, that's 0. That means you accept. Otherwise it's outdated. Okay, so this to make sure that you receive the message is always up to date. Okay? Why this is important? Because in the internet, when you transmit the data, right, some data might be lost, or some data you go in another way. Instead of going shortest path, you choose another path. Okay, let's say you send two messages. You send the first message and you label it 1. Okay, and then you send the second message, number 2, you label it number 2. But this one, choose the shortest path. But this one, go in another way and eventually reach. Okay, so you receive 2 first, that means 2 will receive 2 first, and then you receive 1. So you know now that 1 is actually the earlier one, 2 is the latest one. Okay? If these are the two messages which are the same, of course you only look or read the latest message. You don't read the whole message. Okay? So that is the use of this sequence number. Okay, is to indicate whether you're receiving an outdated request, that means old request, or a new request. Okay? And that's why you need this array. This array is to keep track. Okay? What sequence number that you have received so far. If you are receiving the latest one, you will be inside it. Okay? If you are receiving any old messages, you can compare with what you have. Okay? If it is smaller, then you know that is outdated. Okay? If it is bigger, then you know that is the latest one, and then you update it or you accept. Okay, so that is the sequence number. Okay, let's move on. Now, suppose 5 is the token holder. At the moment, 5 is holding the token. And 1 needs to find the token, but it doesn't know who to get it from because it's oblivious. Okay, what it does is it sends to all. Of course, it needs to know all the sites. Right? So it needs to know site number 2, site number 3, site number 4, and site number 5. It needs to know all of these sites. And then it sends every one of them one message. And this message is always all the same. The first number is its own ID. The second number is the sequence number. So initially it starts with 0. Right now it becomes 1 because it's set to 1. And it's sent to all 1. Okay? Okay, then all the notes will receive. Note number 2, note number 3, note number 4, and note number 5 will receive the message. Okay? And then they will check. It says it comes from ID 1, site number 1. So you will check here. Okay, let's say site number 3, receive it. You look at the message, you see a 1, then it knows that it has to compare with this. Okay, because this is belonging to site number 1. And they look at the sequence number of the message. The sequence number is 1 and it's bigger than what it has. That means this is not outdated. This is the latest one. Okay? So you accept it and you update it. So you will update like this. If it is bigger, that means it's going to update. You will accept all of them and all of them will be 1. Okay, let's see that get updated. Okay, this is how it gets updated. Okay, next. Okay, this is the one that I mentioned. Token is held by site number 5. Okay. Okay, after receiving this, 5 also receive it, and it has the token. Suppose he has done with the critical section. He's already executed the critical section. Now it's not useful anymore to hold the token. It knows that somebody is requesting it. So site 5 is going to pass the token to whoever wants it. And now site number 1 requests it. So you send it to 1. Okay, so what does it do? First, you look at the request and it sees that it is not in the queue, it's only in the queue. Okay? Alright? And then because nobody else in the queue, right? So this is the only one that is waiting. So you remove it and then send it to site number 1. Okay? Now he has to put it in the queue first, right? Because this one is simple example, you kind of say you put and then you remove it. Because later on I'll show to you, if let's say there are multiple requests, then this queue will be full. Okay? You'll have a lot of numbers inside there. So when you add to the back, not add to the front, add to the back. So when you remove from the front, the one that is waiting first. Okay? The longest waiting one will get the front. So you remove the front. But in this case here, this is very simple. When you add, there's only one. When you remove, you also remove the one. Okay? So you have to add first, then you remove. Okay, you add and then you remove. And you find out it's site number 1 because there's only one that's waiting in the queue. And you send this token to site number 1. Okay? Okay, site 5 sent to 1, and right now you can see 1 has it. Okay? Okay, so once 1 receives it, it can enter into the critical section. Okay, it can execute it. So once it executes the critical section and it comes out for the critical section, it will have to update this last array. Okay, this last array is an array to find out whether there's any new request or not. Okay, because you request, but then it can be old requests that you have already served. You want to find out whether this request has been served or not, and you need this last array. And I'll show to you how it works. But for the moment, we update this first. Then we update this last array, and this last array is going to be updated as shown there. Okay? So once you use it up, and then you will update it from 0 to 1. Okay? So that means the request 1 has been served. Okay? What I mean is this. If you see, this is the request, right? And site number 1, the sequence number is 1. Okay? And then if this is 0, if you see this is 0, it means that this request has not been served yet. Okay? Now, if you already served this request, then this one will be 1. Okay? 1 means you already served this request. Okay? So you need to differentiate whether you have already served or not served. So this array is to keep track of. This request array is to keep track of who is requesting. Okay? Last means you want to check whether the request has been served or not. Okay? If the number matches, that means has been served. If the number is smaller, that means has not been served. You have to serve it. Okay? So in this case here, because it already used it and has been served, you have already entered into the critical section. So site number 1 will update. It will update itself, update this LN to 1. Okay? Okay, now we want to show more complicated one. Just now it's too simple. You cannot see the need for all this LN, RN, and also the Q. You'll see why this 3 elements is important in this scenario. Just now it's too simple, so you cannot see the importance of that. Okay, suppose site number 2 owns the token. Okay, it's hold the token. And after they exchange the token, and currently the sequence number is like that. Okay? Everybody has the same view of the sequence number. Okay? That means after exchanging many times, we get into this kind of situation where we've got site number 1 already requests 5 times the token. This site number 2 requests 3 times, 4 times, 2 times, and 7 times. Okay? Right? And right now, token 2 actually holds, site 2 holds the token. Okay. Suppose site number 5, request for the token. Site number 5 is this one. So it send the message. So it send its own ID, and then it send also the sequence number. Just now it was 7. Just like the rest, it was 7 before. Because it sent a new one, you have to increment it by 1. So you have to put 8 there. And itself also 8. So it send out this message, 5, 8. 5 is own ID, 8 is the sequence number that is asking for. Okay, so it's sent out to all. And of course 2 will receive it as well. 2 is the one that holds the token. The rest actually don't hold token, but then they will receive it as well. And they have to update their request array. Okay? The same thing like what I mentioned just now. Because the sequence number 8 is bigger than 7. Yeah, bigger than 7. So they will accept it. Okay, once they accept it, they're going to override. Okay, override it. Let's see. Let's see override. Okay, override, because all of them find out that is new, it's not outdated. Okay, next. Just now was site 5. Right now, site number 1 also want to request. Okay, you want to request as well. So you send 1 because it's own ID. And at the moment, actually it was 5 before, it was 5 days before. So when you send out the message, you will send it 5 plus 1, so it's 6. And you update itself to 6. And you send it out. Okay? And everybody will receive, including site number 2, which is holding the token. Okay, what all of them will do, they will do the same thing. They will check whether the request is outdated or not. And all of them find out that it's not outdated because 6 is bigger than what they hold there. Okay? So it's going to update it to 6, including the site number 2. Okay, all of them update to 6. And next. Okay, just now was site number 5 request, site number 1 request. Right now, site number 3 request. So there are 3 of them that is requested. So site number 3 is, before it was 4. Okay, when it's sent out, you attach its own ID and then you put 5 because 4 plus 1 is 5, right? So you update itself to 5 and then you send out this message. Send to all because it doesn't know who actually hold the token. So you send to all. And the same thing, because all of them find out that the sequence number that is sent is bigger than what they hold, they're going to update it as well. Okay, so all of them is going to update this to 5 and then accept it. Okay? So updated. Okay, now suppose it's done already, everybody, whoever wants it, already request. So 3 sites requested. Just now, site number 2 was holding it, and it was in the critical section. It was busy doing its critical section. Now, when it comes out from the critical section, now it's ready to pass the token away. Okay? So before it passed, it has to check first. It has to check whether all the requests has been served or not. While it was busy just now, right? So you need to find out whether it has been served. So how does it find whether it has been served? You look at the last array and compare it with the request. Okay? So let's see how it does it. And now the rule is this. If the request number is the same as the last request plus 1, that means that has not been serviced yet. That means outstanding. Outstanding means it hasn't been serviced yet. Okay, you can see that this is smaller, right? Remember I mentioned to you, if this is smaller than that, that means this has not been served yet. If it is 1, 1, that means it has been served. Okay, so you check that is. If let's say this is 0, this is 1, right? So 0 plus 1 is the same, isn't it? If the same, that means it's outstanding. That means it hasn't been serviced, so it has to be serviced. Okay, any other condition that is not satisfied. Only this one is satisfied. Okay, so you have to check. check the last array, compare it with the request. Okay? Okay, you come into this kind of situation. This is on site number 2. You see here 2. 2 means site number 2. Okay, site number 2, you receive the message from site number 1, site number 3, and site number 5. Remember? Okay. So site number 1 request, and you update itself to 6, but before it was 5. Okay. Before it was 5, then when you add by 1, you get it equals 6, right? That means actually that request is new request, and you have to service it. So because it's true, you put this site into the queue. Okay. So right now, maybe I have to write it down because it's not clear here. Let's write it down. Site number 1 is 6, 3, 5, 2, 8. Right? So this is site number 1. Okay, site number 2 is 6. All of them are the same. Right? This is all the sites. Or I should put it on it. Okay, how about the LN was just now it was 5. Okay, 1, 2, 3. This one was 4. This one was 2. This one was 7. Okay, how do I know that? If you look at the earlier on, here is 2 minutes. Let's look at the earlier on. Okay, it was like that, right? Earlier on, 5, 3, 4, 2, 7. So earlier on was like this. That means before this one has been serviced, all of this service. That means Rn was this value as well. So Rn and Ln is the same. That means all of them have been serviced. Okay? But after 1 sent to 2, 3 sent to 2, 5 sent to 2, they get into this kind of situation. Okay, that means they get updated into this. Okay? So let's see this page here, because this one does not show to you what it was before, so I write it down there. Okay, so right now it does the comparison. Okay, this one get updated because site number 1 requests, site number 3 also requests, and site number 5 also requests just now. Site number 2, site number 4 did not request. Okay, so site number 2 will do this comparison. You find out 5 plus 1 is 6. That means this is a new request. So in a queue, is a queue, you will add this site number 1 in because it is not serviced yet. Okay, 5 here means this is not serviced yet. It has been serviced, then this one will be 6. Okay, then check this. This 3, so it's not request. This guy is not request. And it checks site number 3. Site number 3 is 5. Before it was 4, so it's not service yet, so you put 3 there. Okay. Site number 4 is the same because it did not request. That's why it must be the same. So it will be false. And then you check this. This 8 is 7. 7 plus 1 is 8, and therefore this is a new request. So you go to put 5. So all these are the requested just now, right? So basically, the site use these 2 array to find out how far already they are into this exchanging of this token. Okay, and they use these 2 also to find out who has been serviced, who has not been serviced, or which one is actually the new request. In this case, you can find out that 658 is the new request because before it was 5, 4, 7. Okay, so you put it in the queue. Alright, so that is this step there. So once the site get out from the critical section, it will do this. you compare these two, and then from these two, you find out who actually requests and you put into the queue. So you found out site number 1, site number 3, site number 5. Okay, so right now it's ready to pass the token, and you pass to the first one. So you're going to remove this from the queue, and then send it to site number 1, because the first in the queue is number 1. Okay? So this is what it does. Okay, you remove, so it's 1. And then you send it to site number 1. So site number 1 will receive it. Okay, you receive the token. And site number 1 right now can enter into the greeters section. Okay? Right? So the queue is right now 3-5. Huh? 3-5. Okay, here is, we want to discuss a little bit just what we have done just now. Remember when we do the comparison and then we add into the queue? We add into the queue not in the order of the requests. Okay, not in the order of the request. The request actually was 5, 1, 3. But when we put in the queue, we put 1, 3, 5. Okay? So it can be a problem because we don't serve it in the correct order. Okay? So this is one of the weaknesses of this Suzuki Hasami. But even though they are not in order, but it's guaranteed that it will not cause any starvation. Meaning that if let's say site number 1 keep on requesting it, okay, site number 1 keep on requesting, but it's always number 1 here, right? Okay, once it gets served, you get up from the queue, but when it comes back, you go back to the queue at the back here. So it will be added at the back. That means all these need to be served first before it gets to be served. That means if it gets served initially, when it comes back the second time, it will be queued at the back. So meaning that with this queuing system, although they are not served in the correct order, but it's guaranteed to not starve the rest of the requester. Because initially when I find the site that is requesting, I look at I start from the beginning, right? So from the site number 1 until site number 5. So when I put in the queue, it will be 1 first, then 5 later on. Even though 5 comes first, right? So actually it's talking about that for this page here. Okay, it's talking about that. Okay, next. So once we already received, this is site number 1. We are looking at the site number 1. It has this queue as well. This queue has been passed along with the token. The queue is having 3 and 5 because served. Site number 1 has been served. Right. So site number 1, once you get out from the critical section, it has to do some update as well. It has to update this because it already serviced itself. Right. Before it was not serviced yet, so it's 5. Now it has been serviced. It's going to update this to 6. Okay. So when it comes out, it's going to take this R6, sorry, R1, which is 6, and put it into here, which is this one. So it's going to update from 5 to 6. Okay. So why does it need to update it to 6? Because it has been served, alright. Remember I told you that this number must match, and when it matches, it means that it has been served. Since site number 1 already been served, so it's going to update it to 6. Okay, so 6 and 6. And that's what it does. Okay, next. Site number 1 needs to find who is the next one, right? So we find from the queue, and the final one is 3, so it's going to remove this. Okay, remove that, and then it send the token to site number 3 together with this queue. This queue is 5, contains 5, and it will send to this site. So site number 3 will hold the token, and the same thing, it will enter into the critical region, and it can do the service. Okay. Right. Okay, the same thing, whenever it comes out from the critical region, it will have to update itself as well. So once it's already serving itself, you convert this to 5. Okay? And then you remove this 5, and now the queue is empty, and you send token to 5. You send the token to 5. I'm not going to play the video already. And once 5 receive it, the same thing, it will use the token and enter into critical region. Once it comes out, it will also update this number. So it's going to update. Okay? And now the queue is empty, so it knows that nobody is requesting it, so it holds on it. So site number 5 will hold on it, even though it doesn't use it anymore. And you can see from here, the RN and LN is now the same number. That means there's no outstanding request to be served, and therefore the token is not going to be passed to anyone, but it holds it. Okay, it holds it until somebody else will come along and then request for the token. And because of that, it will be in a queue, and then site number 5 is going to remove the site number from the queue and service it. Okay, and pass along the token. So this is how actually Suzuki Kasami works, using this key element. The first one is a request array. Second is a last number array, or last sequence number array. And then the third one is the queue. Okay? And it uses the sequence number to determine whether it is outstanding request or not outstanding request. And it uses these 2 arrays to find out whether the request has been serviced. And it uses this queue to find out who is the next to service. Okay? So how does it create the queue? You compare this. If there's a mismatch, that means this number is smaller than that, then it will be eligible to place into the queue. Okay? Once you get out from the critical section, you update itself. That means it has already serviced itself, and therefore the number should be increased to match. Okay? Once it matches, you know that it has been serviced. Okay, that's how it works. Okay? Now, if you read the lecture slide, it's a bit confusing. I suggest that you use this video to understand how this Suzuki Kasami works.
Is there a maximum number for that?
No, there's no maximum number. This number is going to increase to a certain number. Okay? Now, of course, up to a certain point, because integer is of certain size, right?
Yeah.
There's a way, but it's never discussed. There's a way to actually reset it to 0. Okay? So all of them will announce that we need to reset. Everybody will reset to 0 and we start over. Okay? But it's not discussed here, and we don't have to worry about that. We just need to know how actually Suzuki Kasami works. Okay? Okay. Actually, there's some more explanation, more detailed explanation. I'm not to go through it, because I think I already explained quite clearly here already. What I explained here is basically re-explaining what I mentioned to you. Okay? You can watch if you want to, but I'll stop there. Right? So that is Suzuki Kasami algorithm. I use this because I find the slide is very hard for me to explain. I can explain using example much better. Okay, here basically explaining what I mentioned to you just now, with some kind of very difficult way to describe it. We just want to use a mathematical expression or mathematics notation, but basically it means what I just described to you. Okay? So I'm going to skip all this. Okay, next we are going to talk about Raymond's algorithm. So, what Raymond C is this. First thing is, the node is oblivious of all the nodes. Just now I showed only 5. So every one of them have to send or broadcast the message to all the sites, and this can be a problem. If I got 1 million sites, I have to send messages to all 1 million sites. So that's one problem. Can we find a way that we only send to as minimum as possible? We don't want to send to all sites. Second thing is the order of service. 5 appear first, the request first, but 1 gets served first. It's quite unfair, right? Can we find a way that 5 will be served first? In order, 5, 3, 2. Okay, so this is what Raymond proposed. He said, I will use this kind of algorithm where we form a tree. Now, whoever owns the token is going to be the root. So the root of the tree will be holding the token. Okay, that's why it's called Raymond's tree-based algorithm. Okay, tree-based is because it looks like a tree, right? But inverted. This is the root. If you invert it, this is the leaf. Okay, so if you look from the top down, this is the root, this is the leaf. Okay. And if you see here, everybody is actually pointing to the root. Okay? And the children has only one parent. Of course, the parent can have multiple children, but the children itself have only one parent. Okay? So that is a tree. Now, one thing good about this is this. If let's say this is 1, this 1, this 2, this 3, this 4, this 5, this 6, 7, 8, 9, 10. See that? Now, suppose 6 is requesting for the token. He wants the token. What it needs to do is not send to all, but send to the parent. Okay, send the request to the parent. And the parent is not the root. The parent itself will relay the request to its own parent. And its own parent happens to be the root. And right now, the root will receive the message. Okay? And you can see that the message only get relayed. Okay? But then, only one message. Instead of sending so many messages, you only send one message. It doesn't send 100 of messages. Okay, only one. Here you got 10, right? It doesn't send 10, it sends only one. And where does it send to? It sends to the parent. Now, why it is in the form of a tree is because this tree will eventually get to the root, right? And remember, the root is the token holder, right? So here, actually, the tree actually shows to you where the root is and where the token is. Okay? It's always pointing to the root and it's always pointing to the token holder. And when you send a message, you send to the right person. Okay? First, you send to your own parent. Your own parent is not the root. The parent is going to send to his own parent, and this parent happens to be the root. So eventually, this root is receiving the message. Okay, another good thing is this. If let's say 6 send a message, and 5 also send a message, 2 of them wanting to request for the token at the same time. Now, 2 receive these 2 requests, but you only send 1 request to the root. Only 1. Okay? Even though here 2. Suppose here you got 100 of them, let's say at the bottom 100 of them, request at the same time. But when you get to here, this 2 is going to request only 1 time. So you actually compress all the messages into 1. And then send that 1. And you don't have to send so many. Right? So 2 things that improve here. First thing is you don't have to broadcast simply to everybody blindly. Second thing is you know who actually you should send to. The third thing is the message gets smaller and smaller. Even though here you got 1,000 requests, but when you converge, you will send out only one. Okay? So that is the advantage. Okay, because this video, again, this slide does not have any good explanation, I'm going to use this video. Okay, but luckily this Raymond's algorithm is very simple, so I'm going to go fast because I've got only 9 minutes. Now here we got 8 sites. And these sites here is arranged according to the tree that I was talking about. So root is at 2, and 2 is actually the token holder. Yeah, 2 is token holder. Everybody is pointing to number 2. Right? Okay? Okay, one thing I don't quite like about this example is it uses site number and also it uses an ID. So I explain to you. Okay, there's a holder here. A holder is actually a pointer pointing to the address. So this is the address. This is the site number and the address. Actually, they should have used the site number as the address as well. Okay? So let me go back here and explain a little bit about this. Okay, just now this was pointing here, right? This one pointing there, and then it is pointing to 2. So this holder here is a pointer. It points to the address, not the site number, but the address. This, we can assume that this is an IP address, okay? The IP address of this site is 6. So holder here is pointing to this IP address, 200, okay? And then this 6 is pointing to 8, and the IP address is 100. So that's why the holder here, or the pointer, is 1,000. The same thing, 8 is pointing to 2, and the address is 5,000. That's why the holder here is 5,000. Okay, the same thing here. This 7 is pointing to that, that's why the holder is 1,000. Okay? So you can just imagine that there is some kind of pointer pointing to it, but it's not shown here. Okay? Okay, this one explains what I explained just now. Let's move on. Okay, let's say, for example, 7 requests for the token. So you send out a request. When you send out a request, you put itself into the queue. So everybody has a queue. Okay, this queue is to keep track of who is actually requesting. And why you need a queue? Because imagine 8 is the parent of 7 and 6, and also the grandparent of 1. If all of them request, then you have to queue it up because 8 needs to know which of these children here is requesting for the token. So you have to queue it up, right? And the order of arrival will be the order of service as well. So the queue is helping to do that. Okay? So you put itself 7 into the queue, and 8 actually is not the root. So it has to send to its own parent, which is number 2. And because 7 was requesting for it, so you have to remember who actually requests for it. So you put 7 into its own queue and send the message to root, which is 2. Now 2, after it has used this critical this token, we have already entered the critical section. Now it's ready to pass the token. Okay, it's ready to pass the token to node number 8. Okay, so that's why you put 8 and because 8 actually requests, so you put it inside. Once it's done with the critical section, okay, it's ready to pass along. And what it does is you pass it. Okay? So once it passes it, it actually removes. And how does it know who to pass to? You remove it from the queue. The queue shows 8. And that's what is sent. Okay? And the queue is empty right now. Okay, the same thing. Site number 8, because it's not requesting for the token, right? So it looks into the queue, and the queue says 7. So it knows that this token must be sent to 7. Okay, it pass down to 7. And we remove it from the queue. Okay? Okay, and node number 7, it looks at the queue and find out its own self. So it knows that it is the one who is asking for it. So you remove it and then use it. Okay, remove it and also use it. Okay? So that is a simple example. Now, take note, as we go along just now, here, okay, when 2 pass the token to 8, its token holder just now was pointing to itself because it's pointing to itself because it's the root. You can see that this guy is pointing to the root of 5,000. But 5,000, the token holder is 5,000, and it's pointing to itself, meaning that he is the owner of the token, the root. Okay? And when it passes this token to 8, you see this token holder here is going to change. It changed to 1,000. When it changed to 1,000, why does it change to 1,000? Because 8 right now is the token holder. Alright. So right now, 8 is the root. Everybody is pointing to this 8. Okay, so this guy is pointing there, and 2 is pointing to 8. And 8 right now is the token holder, is the root right now. Okay? And because 8 is not going to use the token, it sees from the queue, 7 was one request, and it sent to 7. Look at this holder here. First, it was pointing to there. Right now, it will point to 100. Okay? So it's point to 100. Point to 100. That means this is the root right now. Everybody is pointing to this root, including this one. This one is pointing there, and this is pointing there, and this one is pointing there. So root is number 7. And you will see later on, this one will change to 100 as well. It points to itself, it means that is the root holder. Token holder. Okay? Okay, 100 there. You can see that is a token holder. So that is the end for this. But this one is a simple example. Let's look at a more complicated one. Now suppose this is the token holder. So this is the root, right? Everybody is pointing to this guy. And site number 5 requires that send a message to 3. And because it requests for it, so it put itself inside its own queue. Okay? And 3 is going to receive, because it is not the requester, it's going to pass along. But before it passes, you put 5 into the queue to remember who is the requester. And then it passes that message to 2. And 2 is not requesting for it. Before we go to the next one. Site number 4 requests, just not site number 5. Now site number 4 request for it. So it puts itself inside the queue and then send the message to site number 3. And site number 3 receive it. And this time, because it sees that it has already sent the message, right? How does it know? Because the queue is not empty, so it must have sent the message to its own parent. So it will not send any more messages. Okay, instead it will just queue number 4. Okay, only one message has been passed just now. Okay, one message passed because of 5, but when 4 comes, because 5 is there, that means it knows that the message has already been sent to 2, it will not send again, and it will just put 4 in the queue. Okay, so right now it knows that 5 and 4 is requesting for, or it remembers 5 and 4 is requesting for the token. Okay? Okay, and it itself wants to request for it, so 5, 4, 3. Okay? Now, site 2 receive it, and then it will pass along to its own parent, and its parent sees it and pass along to 7, and along the way you also update the queue. Okay? And then you do the rewind. So because this guy is no more using it, pass to 8, 8 pass to 3, and this one is pointing back to here, and 8 is pointing to 2. And right now 2 is pointing to 3, so 3 is right now the root. Okay, you remove from the queue and serve 5. Okay, and then it requests again. It pass to 5 and it requests again. Request, sorry, request 3. I think there's a mistake just now. Yeah? The 3 should not be removed, but it get removed just now. Once if have been received and then it requests, that's why you see a 3 there. Okay? And then it return back this because it's not the itself yet, it's number 4, so it's set to 4. Okay, once 4 finishes, it return back to 3. And 3 will use it. Okay, you can see that 3 actually is quite disciplined. It knows that it did not request early on, it request last. So it passed the 5 and 4 first before it uses it. Understand? So the order of a service is as what it was requested. Okay? So this is Raymond's algorithm. And basically they are all token passing algorithm. And that's how they pass the token around in order for each one of them to use the token and access into the critical section. Okay? Okay, I know that this one is very hard to explain because it's very lengthy. But if you miss it, I suggest that you watch the video. Okay? The video actually shows you how it works. Okay, I'll stop here because we finished up already. I'm going to continue this next week. This one I already explained. Next we're going to talk more detail about deadlock. And then how do we do deadlock avoidance using this banker's algorithm. Okay, we're going to talk about this banker's algorithm next week. And banker's algorithm is also coming out in exam. So please come attend the class. I'll explain to you. And also I sent to you this. Maybe you can watch this video first. Okay, the one that I put up is one of the easy to follow YouTube. Okay? And this is also the same thing. I found that he explained quite clear. Okay, you can actually look at it first. This algorithm is also quite lengthy, so I will take some time to explain it. And this question, there's a one question, one complete question on the banker's algorithm. So I suggest that you go through this. Okay? Now the question is 25 marks, and if you follow, actually it's very simple. You just need to know the steps on it. Okay? If you follow, then you should be able to answer this question. Okay? The question that was set was not so difficult. So please have a look at it first before I explain to you next week. Okay? Okay, we end here. I'll see you next week. Because I received a message I did not have time to reply. I will move it to week 8. There's a request because I think you all have midterm. Is it 3 midterms?
Yeah. So the proposal assignment also can be for next week Friday or after Saturday better.
Friday. Next week Friday.
Sunday cannot.
I put Sunday, isn't it?
You put Monday.
I put Monday. Okay, I'll put Monday. Because I don't want it to be too late. Don't want it to be too late. So the proposal, I'll change the date as well. And the midterms, I also change to not next week. It will be week number 8. Week number 8. Okay?
Online.
Yeah, it's all online. It will be night time as well. So online, night time is open book test, but please study first before you come for.
So this one will come out.
You will cover until here.
Until here.
Okay.
So until cover until today.
Until Raymond's algorithm.
Until
Right?
which algorithm?
until Raymond's algorithm.
And so the proposal due date is next Sunday, right?
I'll put it in the now message tonight. Okay, I'll send it tonight.
Thank you, sir.
Please have a look.
And so
Oh yeah, attendance. I will mark attendance.